So you guys have been doing great, and it turns out there's just a short video today. There's only going to be 3 slides in today's video. Next time we'll spend more of the time to practice naming compounds and balancing compounds and stuff like that. But there's a few more things we need to talk about. We've talked about ionic and covalent bonds. There's one more type of bond to form I'd say into a compound. It's not exactly a compound, metallic bonds, but it is a third type of bond we can talk about. And then forces that act between compounds, particularly molecules. So a metallic bond. It turns out that metals have a lot of empty or partly filled orbitals. They have their d orbitals, and group 1 metals, for example, have, some s orbital and then the whole p orbital that's empty that they can fill with electrons. So when these orbitals overlap in these metals, when these metals come together to form what we would think of as metal, like a sheet of aluminum, electrons can flow freely through these empty or partly filled orbitals and go from one atom to another pretty easily. The common metaphor used to describe this is a sea of electrons. Imagine each of the atoms as a little island, and the water going around the island is the electrons. They can just move back and forth from one atom to another. This is going to be able to lead to all those properties of metals that we've talked about. Most importantly, conductivity, because these electrons can freely flow from one to another. It's going to help explain luster. It's going to help explain malleability and ductility. This metallic bond is very special, and it's going to form between two, that could be the same sort of metal, a bunch of atoms of that, could be a bunch of atoms of 2 metals or even more metals. Because we can form what's called an alloy. An alloy is a combination of a metal with other elements. Those other elements could be metals. Those other elements could be nonmetals or metalloids. And the resulting mixture of that is going to have a mix of properties. Bronze is one. Bronze, you may recall, is going to be an alloy of tin and copper. Bronze was the alloy that really allowed humans to move out of the Stone Age, making tools out of stone, and start making them out of metal. Bronze is a metal that was strong enough that you could make things out of it, primarily weapons, but also other tools, plows, and such. Steel is another good one. Iron by itself is really rust very easily, and it's a little bit too soft to make good tools out of, again, either weapons or farming implements or really anything. But if you mix steel with carbon, that's going to change the properties enough so that steel becomes more useful. Steel is a mixture of iron and carbon. It's an alloy. So that's going to do it for metallic bonds. Now, polar bonds. We talked about these a little bit before. This is a special type of covalent bond because think back, what is covalent bonding? And right, covalent bonding is where these two atoms are sharing the electrons, but the problem is they don't always share completely equally. So if they're not sharing completely equally, one of these atoms wants the electrons more than the other one. And you'll recall that that's due to the property of electronegativity. So if it wants them more than the other, it's going to drag them towards this side. This diagram here, the red is showing that the fluorine in this hydrogen fluoride, also known as hydrofluoric acid, actually has more of the electrons on its side. This is going to result in what's called a dipole. Dipole, just think of that like a magnet, where you have a north end and a south end. You're going to have a partial positive charge and a partial negative charge, because although these electrons are being shared, it's not an ionic bond. The fluorine wants the electrons more, so it is going to be more negative on the fluorine's side, the side right here. That's going to lead to all sorts of interesting things. Because since we've got a slightly positive side and a slightly negative side, if this comes into contact with another molecule that's similar, negatives and positives will attract to each other and we'll have what's called an intermolecular force. Most bonds have some amount of ionic and some amount of covalent nature to them. A true covalent bond would have to be the electrons being shared 100% equally, and that's rarely going to happen. Usually one of the atoms is going to want those electrons more than the other. So, intermolecular forces then. These are attractions between molecules. Inter is going to be between. So how does this work? Well, these bonds are always, first of all, going to be weaker than either ionic or covalent bonds. Those are intramolecular forces. I guess technically only the covalent bonds would be an intramolecular force because only covalent compounds are molecules. But it's going to be weaker than an ionic or covalent bond. So, the first type of intermolecular force that we can have between molecules is going to be a dipole-dipole. So in the case of hydrogen fluoride on the last slide, you've got one thing that has a positive and a negative side. You've got another thing that has a positive and a negative side. They're going to be attracted to each other, the positives to the negatives, just like putting two magnets next to each other with their north and south sides. That's called a dipole-dipole attraction. A very special type of that is called hydrogen bonding. Hydrogen has a fairly low electronegativity, and some atoms, particularly fluorine, oxygen, and nitrogen, are very electronegative. They're going to very strongly drag those electrons towards their own side, giving the hydrogens the positive charge, the oxygens a slightly negative charge. Those oxygens are going to then be attracted to other hydrogens. This is called hydrogen bonding. It's very, very important in water. It explains why water has a high boiling point, and why water has high surface tension, and why water has cohesion and adhesion, all these things that you learned about in biology that makes water special. You can also have an attraction called a dipole-induced dipole. Now let's say that you've got, again, let's go back to hydrogen fluoride. The fluoride has a slightly negative charge on its side. Let's say it moves close to something that is nonpolar, something that doesn't have a dipole. Let's say hydrogen gas, H2H2. It's completely perfectly shared. But that negative charge on the fluorine, if it gets close enough to that H2 molecule, it's going to push the electrons to the other side. And that's going to give that hydrogen molecule a temporary dipole. There's a good picture of this in your book on page 206. We'll also talk about this in class next time. It's not as strong as a dipole-dipole. And then there's also something called London dispersion forces. This is going to help us explain why even something like two atoms of neon, noble gases, that are just happy by themselves will still be attracted towards each other. So let's think. The electron cloud. In this case, we've got the electrons all moving about randomly, right? Well, if they're moving about randomly, then there will be a situation where occasionally there will be more electrons on one side of the atom than the other. What happens when we do that? Well, now one side has a slight negative charge and one side has a slight positive charge. This again is going to act as an temporary dipole, an instantaneous dipole is the word. And that's going to work just like the dipole-induced dipole attractions. These things will be attracted to one another. Again, we can sketch it out in class again next time, but you can look on your book. I believe page 207 has a picture of that. Why do we care about intermolecular forces? Well, depending on how strong these forces are, it's going to lead to differences in melting points and boiling points of compounds, because the forces that hold them together, in order for something to melt, it needs to break free of the things next to it. In order for something to boil, to go from a liquid into a gas, it's going to have to break free of the things next to it. And the harder it is to do that, the higher the boiling point will be. That's it for today. Thanks for listening.